What was the last thing that we did today morning? We are actually in the morning we are doing 2 exercises, and both the exercises we left in the midway, right? Okay, so the first one was that if you are given a Hermitian form, so given a Hermitian or a symmetric form on a complex or a real vector space V respectively, there exists a basis of V with respect to which the Gram matrix is of the form IP minus IM OZ. Moreover, these numbers P, M and Z are unique. That is, if there is another basis with respect to which the Gram matrix is of this form, then this P, this M and this Z won't change. Okay. So, moreover, the numbers P, M and Z are uniquely determined, or the triplet actually, sorry. P, M, Z is uniquely determined by the form this. That is, if you take another basis with respect to, another orthogonal basis of V, this form of the matrix will not change. It will, if you not only take a orthogonal basis, if you club the plus ones, minus ones and zeros together, you will get exactly this form. So, in the proof, we have shown that indeed there exists such a basis for which this is true. So, how far we did proceed. So, we have already shown that there indeed exists such a basis with respect to which the form is, the Gram matrix is, the matrix has the required form and what else, and Z equal to dimension of phi perpendicular, P perp. Okay. That in particular implies that P plus M is fixed, right? Because P plus M plus Z is equal to N, and if you know what is Z, what Z is, then you know what P plus M is. Now we are trying to show that P is uniquely defined. Okay, that would in particular imply that M is uniquely defined. Okay. So did any of you figure out how we should show that? It is the next step. So next step was to show that P is uniquely determined by the form. Okay. So Sairam already gave an argument after the last class, but any of you also tried this? If not, let's just see what the argument is. Basically, we have taken two bases B as V1 dot 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 Vp and then Vp plus 1 dot 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 Vp plus m and then Vp plus m plus 1 dot 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 Vp plus m plus z, that is n. Okay, for which this matrix had this form. Okay, so with respect to this, the Gram matrix of the form is Ip I minus Im and 0 z. Okay, and suppose we have B dash, another orthogonal basis, V1 dash dot 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 Vp dash, okay, and Vp plus 1 dash, P dash, V dash P dash and V dash P dash plus 1 dot 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 V dash P dash plus M dash comma V dash P dash plus M dash plus 1 dot 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 V dash P dash plus M dash plus Z dash. Well, Z dash should be equal to Z because Z or Z dash both will be the dimension of V part, right? So it will just be Z. Okay. All right, with respect to which GB dash, the Gram matrix with respect to this basis of the form would be I P dash minus I M dash and 0 Z. Okay. We are trying to show that this P dash and this P would be equal. Up to this, all are with me? Okay. All right. So what we would do, earlier we have shown that if you take V1 to Vp and V dash to this one, I mean V dash P dash plus 1 to V dash P dash plus M dash, yeah, P dash P dash plus M dash, that is the one corresponding to this part, then this and this are linearly independent, okay, together they form a linearly independent set. Now instead of just taking that one, you can consider this thing, okay. Consider say V double dash, which is V1 to Vp, and then the other part we are taking from that basis. So we are not only taking this part, we are taking this together, okay, also the 0 part. So V dash P dash plus 1 dot 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 V dash P dash plus M dash, and then V dash P dash plus M dash plus 1 dot 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 V dash, we can just write N, right, okay, because N is equal to P dash plus M dash plus Z. Now the claim is that this is a linearly independent set, okay, and the proof is exactly similar as we have done earlier. Okay. Suppose they are not linearly independent, then there is a linear combination of them which is equal to 0, and you can separate out this part and that part. Okay. So that would give you, so if B double dash is not linearly independent, that is if B double dash is linearly dependent, then there exists A1 dot 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 AN, not AN, sorry, a P and B1 dot 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 B M dash plus Z in C such that A1 V1 plus dot 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 plus AP VP is equal to B1 VP dash plus 1, sorry, V dash plus 1 plus dot 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 B M dash plus Z Vn. Okay. So some linear combination, that is this one minus this one, is equal to 0. Okay. That would be a linear combination of this and this, right? So call this one V and just compute this. That would give what? Summation AI squared Vi on the left hand side, I running from 1 to P, which would be equal to here summation, well, minus summation Bj squared V dash j, here dash also, where j is running from 1 to where? J is running from 1 to, yeah, M dash, exactly, because the rest of the things would be 0, right? M dash. Okay. All right. Because here we are not using anywhere whether these ones are orthogonal to this or not. We are just using that they are orthogonal among themselves. Okay. So this is a part of orthogonal basis V1 to Vp, and that's why we are getting this one. Similarly, these ones are also a part of orthogonal basis, so we are getting these ones on the right, and there would be some more terms, but wait a minute, what I am doing here? These are not Vi, excuse me. This will be, these are just, excuse me, these are 1. Yeah, I mean, these ones are the inner product of this with it, these ones are 1, and the inner product of these ones with these ones, I mean, with up to here is -1, and the rest is 0. So the rest is also present here, okay? But those are just Vi, I mean, those ones are like Vj equal to 0, right? So we can forget about those. Okay. So note that this one is a non-negative quantity and this one is a non-positive quantity. So you get that this is equal to 0, right? What will it mean in particular? That all these AIs are 0. Now if all these AIs are 0, that means this linear combination is 0. However, this part of the basis, this was a part of a basis, so these are linearly independent. Okay. So all the coefficients B1 to B M dash plus Z, all of them should be 0. Okay. So that in particular implies that V is equal to 0, and hence that implies B dash is linearly independent. And with that we are done, right? Because if B dash is linearly independent, that would mean that P plus M dash plus Z is less than or equal to N, and n was p dash plus m dash plus z, right? So p dash plus m dash plus z. Okay. Of course, this gets cancelled, and you get p less than or equal to p dash. Similarly, you will get p dash less than or equal to p. So we are done. So this implies p less than or equal to p dash. Similarly, we also get p dash less than or equal to p, and that implies p is equal to p dash, and hence m is equal to m dash. Okay. Now that finishes the proof, and just let's recall that we define signature of the form, this form, to be this tuple p comma m. Okay. Because if you have p comma m, this will also define what is z. It is just n minus p minus m. Okay. And this, this actually is a unique thing given by a form. Okay. Manas, any doubt? Yeah.
I did not understand how if V cannot belong to the span of V1 to Vp.
If V, yeah, if V is in the span.
We proved that if V is in the span of V1 to Vp and it is also in the span of V dash
Right.
to Vn dash,
Right.
then
It should be 0.
it should be
Right.
How does that imply V double dash is linearly independent?
Which one?
How
B.
does that imply
Well, suppose it's not linearly independent. What does it mean?
so there is a linear combination in which not all coefficients?
Exactly. So it's a linear combination of all of these things, right? So you can keep some part of this on the left and take the other side here, and that is giving you such thing, V. Okay. And then we are just proving that that would imply V is equal to 0. Now, if V is equal to 0, that would, so you are getting a linear combination of a set of vectors to be equal to 0. Okay. And now, well, if V is equal to 0, not only that, we are, so we are, till here we have proved that V is equal to 0, and in particular, we yeah, so it's not only V is equal to 0, we have actually shown that all the coefficients should be equal to 0. Okay. And that would mean that this is a linearly independent set. Okay. So in particular, if you are given an orthogonal basis, it's quite easy to get the signature. Just check the signs of these ones. Okay, of your, so V is, suppose V1 dot 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 Vn, an orthogonal basis. Just check these ones. If these are positive, those are corresponding to P. If these are negative, that is corresponding to minus, that is minus Im, M. And if this is 0, those are corresponding to Z. Okay. So it's quite easy if you are given an orthogonal basis. Otherwise, you have to find an orthogonal basis, and that is quite some task because you have to do some procedure like the Gram-Schmidt. Okay. All right. Now about the second problem. Okay. So another exercise, it was that if A is an n cross n complex matrix, say a Hermitian matrix, sorry. such that determinant of AK, well, no, we do not say such that, it was an if and only if condition, excuse me. So the sentence stops here, Hermitian matrix. Then A is positive definite if and only if determinant of AK is greater than 0 for all k. And how we define this AKs, these are the submatrix on the, these submatrices. So this is your entire A, and then the first 1 cross 1 thing is A1, the first 2 cross 2 thing is A2 dot dot dot, the first k cross k thing is AK. Okay. So we are defining AK as Aij I less than equal to k, j less than equal to k, where A was Aij I less than equal to n, j less than equal to n. Okay. So this was our full matrix, and then if we restrict the indices I and j to to the range between 1 to k, that is the submatrix AK. Okay. Okay, so how far did we prove in the morning? If part, that is, if it is positive definite, then this is true, right? And how do we did this? We restricted the basis to the first k terms. Okay. Then the corresponding gram matrix would be just AK. So proof till now we have proved that if A is positive definite, then determinant of AK is greater than 0 for all k. Okay. Now the converse. Now we are going to show that if determinant of AK is 0, greater than 0 for all k, A is necessarily a positive definite matrix. Okay. Well, we start by induction. So for k equal to 1, this just means that the first entry is positive. Okay. And that would in particular mean that A is, A1, wait a minute. Well, if A is an n cross n matrix, so wait a minute. We proceed by induction. Okay. How? Induction on the dimension of A. So if n is equal to 1, the claim is trivial because we are asking that x star Ax is equal to identity. That is, so that would mean whatever, not identity, x star Ax is positive, right? Now A there is just a scalar, okay, and you are multiplying it with the norm of some norm squared of some non-zero scalar. Okay. that means you are multiplying a positive quantity with another positive quantity, our output is always positive. Okay. So if n equal to 1, the claim is trivial. Okay. Assume that the claim holds for n equal to m, okay, for some m larger than or equal to 1. Okay. We are going to show that it holds for m plus 1. So this in particular means at first that if we have this matrix AM and such that all its submatrices have positive, not submatrices, the submatrices of this form, okay, all these are having positive determinant, then AM is positive definite. Okay. So if A1 dot 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 AM all, so induction hypothesis means this implies that if these are all, they all have positive determinant, then AM is positive definite. Okay. Now that would mean that the form that AM defines, that is, if you restrict your basis to the first m element. So wait a minute, what we did earlier, we chose a vector space V and a basis B, and since A is Hermitian, it defines a Hermitian form over V. Okay, Mahfuz, it's all right? Do you recall that? Okay. So let B be the basis of V with respect to which A represented the Gram matrix of a Hermitian form. This B we have chosen, okay? We have chosen it. We have chosen the vector space and we have chosen a basis, and we defined the form on V with respect to this Hermitian matrix, that is defining this Hermitian matrix to be the Gram matrix of the form. Now, if B is of this form V1 dot 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 Vm and Vm plus 1. This is our, so here we are assuming that n is equal to m plus 1. That is, we are trying to prove it for m plus 1 now. Okay. So if this is our basis, then now restriction of the, now Am represents the Gram matrix of the form with respect, on the subspace of V, which is spanned by V1 to Vm. Okay. So let W be the subspace, well, let W be just the span of V1 dot 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 Vm. Then the form is a positive definite Hermitian form on W, right? That implies what? Yes? Because I mean by induction hypothesis we know that AM is positive definite, right? Now the restriction of the form to W gives AM as your gram matrix, right? And since it is a positive definite Hermitian form, in other words an inner product on W, what can we conclude? No, that W has an orthonormal basis. So in particular that means so whenever you have an inner product, you can use Gram-Schmidt to get an orthonormal basis from whatever basis you start with. Okay. So this will mean that W has an orthonormal basis with respect to the given form that we originally defined by A. Okay. That implies that there exists some matrix, say Q, maybe Q dash, in GLMC such that Q dash star AM Q dash is equal to identity. Identity is a gram matrix with respect to the orthonormal basis, and this matrix Q dash is a change of basis from this V1 to Vm to that basis, which is orthonormal with respect to this form. Okay. So now define this matrix Q, which is of this form, Q dash here and all zeros, this entire row is 0, this entire column is 0, and here you are having 1. Okay. Just 1 cross 1 thing. You are extending this matrix, just adding 1 here. Okay. This is m plus 1 cross m plus 1. Okay. Now what we are going to do? We are going to do this. Maybe we write there, okay, on the left side. We are going to consider Q star A Q star, sorry, Q star AQ. And we know how the m cross m part, this one, would look. We do not know how the last row or the last column looks. Okay. But the other part we know very well. Okay. So consider Q star A Q. Okay. This will have the form Q dash star 0 row 0 column 1 A m here, and then here the other entries of A times Q dash 0 0 1. Okay. Now this has m cross m size, this has m cross m size, this has m cross m size. So if you multiply this, you will just get here Q star A m Q, and we do not know much about the other entries. Okay. form like this. Now this one would be identity, right, by induction hypothesis. Okay. So that is I m, well, just I maybe, because we know it is m cross m. Okay, and one, not one here, star. Okay, maybe I am writing m here would just let us remember what is the dimension. And this entire thing is m plus 1 cross m plus 1. Okay. So what we are going to do now? We need an entire identity, right? Now, given this form, what should we do? Something that you have learned very well in the previous semester. Row reduction. Very nice. So we would reduce this entire row and try to make it 0. And we can do that because here is a pivot on each of the columns, right? So suppose E1 dot 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 Ek are denoting the elementary matrices with which we multiply this one to reduce the bottom row to all zeros except this one maybe, because we know that there is a pivot in each of these columns, right? Okay. And name this matrix P. Okay. Maybe you can also multiply Q star with this. Okay. So this one. That is the elementary matrices and Q star as well. We define it P. Okay. And then consider this matrix P. Wait a minute. Let's define rather this to be P star. Okay. I mean, we can of course define it as P star, where because P would be just then bar transpose of this. So that would imply that P star A Q, P star A P would be of this form. Of which form? Here it is I m. Here the entire row is 0, right? And here some C, and this one, well, do we not know these ones or do we know these ones? What do you think? Yeah? Yes. It's symmetric. So if this is 0, these are bound to be 0, right? All zeros. Okay. So if you choose P star of this form, that would imply that P star AP is of this form, as P star AP is Hermitian. Okay. And now we are left with only one thing to show that this C is non-zero, right? Non-zero or positive actually. I mean, if it is positive, we can divide it by its length, right? By the way, what is the signature of a positive definite form? Exactly, n comma 0, right? So that means all the things, all the products, I mean, if you take V1 to Vn, Vi would be positive for all the i's. In particular, it suffices to show that this C is positive. Okay. Now recall what is the assumption. Determinant is positive, right? And that settles this, right? Yes, exactly. Since determinant of A is greater than 0, that implies determinant of P star AP is just determinant of P squared times determinant of A, which is greater than 0. But what is this? This is just C, right? So this is equal to C. Okay. So we get that C greater than 0, and that settles the claim, right? That implies A is indeed positive definite, as its signature is in 0. Okay. All right. So just a few definitions, and then we finish the class. Okay. We do other proofs in the next class. Okay. So now what we are going to do, we are going to use linear operators on Hermitian spaces. Okay. Let T from V to. By the way, do you recall what are Hermitian spaces? V Hermitian space, yes. Tell me what. Not only a Hermitian form, an inner product. Okay. Yes, a Hermitian, a positive definite Hermitian form. Okay. Hermitian space. Okay, so that is a complex vector space on which an inner product is defined, or with an inner product this. Okay. Now let T from V to V be a linear operator. Okay. And suppose we are given if there exists such an inner product, I know that immediately we have an orthonormal basis of the vector space, right? So let B be an orthonormal basis of V. Okay, by Gram-Schmidt this exists, right? Okay, and let A be the matrix of T with respect to the basis B. I hope you still recall how we defined the matrix of a linear operator. Could you just recall how we defined it? Yes. 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 The same basis, because it's a linear operator. Very good. Right. So that means TB is equal to BA. Okay. This A is the matrix of the linear operator. Matrix of T with respect to B. Okay. Now we are going to define the adjoint operator of T. So we know what are adjoint matrices, right? The operator T star, that is called the adjoint operator of T, from V to V is the operator whose matrix with respect to the basis B is A star. Okay. So we know what are adjoint matrices, and this helps us define what is an adjoint operator of a given linear operator. Okay. And once we have this definition, we can extend the definition. We can at first define what is a normal operator, and then see how the definition of Hermitian matrices or unitary matrices extends to Hermitian operator or unitary operators. So, normal matrices at first. What are they? We define them in this manner, that is, a matrix A, a square matrix A, sorry, we mean a complex square matrix is called normal if A star A is equal to A star. Okay. That is, the adjoint and A, they commute with each other. Okay. And of course, you recall what are Hermitian matrices. Unitary matrices. Okay. These were just A star equal to A, and unitary matrices A star or A star A equal to identity, right? Note that this, Hermitian matrices or unitary matrices are just special cases of normal matrices, right? Okay. Similarly, we define normal Hermitian or unitary operators. Okay. So, for example, a normal operator would be which commutes with its transpose. T star is equal to T star T. Okay. A Hermitian operator is for which we have the adjoint equal to itself. T star is equal to T. And an unitary operator if T star T is identity. Okay. Quite simple. Okay. Normal operator, Hermitian operator, and unitary operator we define exactly as we defined the normal Hermitian and unitary matrices. And this one is T star or T star T equal to identity. Okay. So that's where we stop now. In the next class, we would show that the normal operators on a Hermitian space, all the normal operators on Hermitian spaces are diagonalizable. That means the inner product space on which it is defined will have a basis made up of its eigenvectors. Okay. So in the when you diagonalize it, all the eigenvalues of T will appear on the diagonal. Okay. That's called the spectral theorem. Okay. So if you prove it for normal matrices, normal operators, we will prove it for Hermitian. I mean, that will imply it for Hermitian operators or unitary operators. Okay. Thank you.